Hello everyone, this is our Dynamics of Machines term project. From the four given topics, we have chosen the first topic as our project topic, in which we have to analyze the IC engine model. The reason for choosing this topic is that we all are quite accustomed with the internal combustion engine and its working, and we had one third of a whole subject dedicated to this. What exactly we are going to do in this project? We are going to create a 3D model of an IC engine. Then we will check the performance with and without balancing the flywheel, and then analyze the model considering the practical values of masses of piston and the cylinder pressure variation, and then we will plot all these graphs. Now let's check our model. First we will check a basic simple model, and then we will see the actual IC engine model. This is a simple 2D model where the wheel actually moves when rotated by a crankshaft arrangement. This is a 3D model of a single cylinder IC engine. Let's check out the performance with and without balancing the flywheel. Why engine balancing is needed? The first question to be answered. If the engine is not properly balanced, then there will be vibrations in the engine, which will cause damage to the parts. Balancing of the engine also increases the efficiency of the engine, thus increasing the power output. Before proceeding, we need to make some assumptions, and this free body diagram will come in handy in order to properly navigate through the upcoming equations of dynamics. Now we derive two basic equations. One is the force acceleration equation, which we derive from Newton's second law by summation of all forces equals to mass times acceleration. And second is the momentum angular acceleration equation. Now we have to balance the dynamic forces first. Here f of x and f of y are the two main forces which cause vibration. F of x is the force in horizontal direction and f of y is the force in vertical direction. In order to make the machine stable, we need to limit or minimize these forces. In order to minimize the forces f of x and f of y, thus above condition should be hold true. Thus, if we equate this, we get f of y equals to 0 and f of x some equation which has relationship with the angular acceleration of the body. In order to balance the force f of x, that is the horizontal direction force, we need the help of this free body diagram in order to arrive at some conclusion. Once we check out the value of a, the problem is completely solved. But there is only one constraint. This is for if the f of x value has only second order terms. Partial balancing can be done to the engine via a practical approach. It is only possible if this equation holds true and the value of x should be less than the value of L. Let's check our second part of the basic equation where we deal with the terms of momentum and angular acceleration. The above equation has targeted moments which we need to reduce. For minimizing the equation, we need to perform some following substitution and check the result accordingly if it satisfies the conditions. In our first substitution, we can clearly see that the value of A is greater than L, which completely defies and is not possible. Now in this second substitution, which is achievable by proper geometrical approach and construction, thus in conclusion we derive that we can minimize the equation 6, but this minimization cannot balance the engine completely. Some sort of vibration are always present in the engine, which we can clearly see in our daily life. Now let's check the conclusion of the whole balancing process. Balancing reduces engine vibration. It improves the efficiency of the engine. Balancing the engine is very expensive as we need to deal with some geometric parameters which are to be pretty precise. Complete balancing of the engine is not possible. Remaining excess vibration can be reduced by vibration isolation. Now let's have a discussion on flywheel. What is actually a flywheel? A flywheel is a mechanical device which uses the conservation of energy and angular momentum to store rotational energy. Or in simple terms, it is a balanced spinning wheel with a significant moment of inertia. Now let's discuss the case when there is no flywheel. In an internal combustion engine, the resistive moment remains constant, but the turning moment varies. That is, it is positive in case of expansion and negative in case of compression stroke, but partially positive and negative in the remaining two strokes. Since the resistive moment mr is not equal to the turning moment m, there will always be an acceleration in the crankshaft. This graph shows the variation of turning moment with the change in the angle. Now when there is a flywheel, we will calculate the total energy by taking a complete integral, and from that calculated total energy we will find the average momentum. The total angle will change accordingly with the number of strokes and will keep on increasing as the number of strokes increases. This graph shows the variation of turning moment with the change of angle when there is a flywheel present. Now, in order for the engine to work at a constant angular velocity, we must satisfy the condition, which is that the total sum of moments equals to zero, so there will be no angular acceleration. The term project is brought by Samrat Biswas, Muzaffar Hussain, and me, Sheikh Mohammed Farman. This part contains our code and the graphs. I would like to suggest you all to only focus on the graphs, not on the code.